12.3, Double Integrals in Polar Coordinates, Video 3. The following can be found on page 711 in your textbook, Converting a Double Integral to Polar Coordinates. If a function f of x, y is continuous on a polar rectangle defined by the following, then, well, let's look at how the rectangular region is defined. In this first inequality, which looks like it just doesn't end, all it's really saying is your radius is between A and B. What this over here is saying is everything is positive, or rather I should say non-negative. The reason we don't allow negative radii is because when you're integrating, you don't want to go backwards into a different part of the region while you're over here on the positive side looking over there. For your angle, it looks like it just says it has to be between two angles alpha and beta, but there is a restriction on them. The restriction on the angles is that their difference can't be more than 2 pi. And of course it must be positive. Saying the difference is positive is simply saying that this second angle is larger than the first one, or at least no less than. But saying that the difference is less than 2 pi is saying that once you've gone to your first angle, your second angle can't be so big that it goes past a complete revolution. Otherwise, you're overlapping into your region again. So as long as your angles don't differ by more than 1 complete revolution, you're fine. Then to convert the integral, the double integral of the function over that region, dA, and just a quick reminder, in rectangular coordinates, dA is just dx dy. Makes perfect sense. Area is length times width. But when you convert it to polar coordinates, you'll do the iterated integral, where one of the integrals is over the angles on which theta is defined, in this case from alpha to beta. The other integral is defined over the range of values for the radius from A to B. Inside the function, you change x to r cosine theta, which was one of our conversions in the first video. And you change y to r sine theta, which was another conversion in a previous video. But here's the thing that seems to come out of nowhere. The dA in polar coordinates is r dr d theta. Why does that r sneak in? Well, there's 2 ways I can explain that briefly, but not in detail. Number 1, go read pages 709, 710, and it will go into excruciating detail why dA in polar coordinates has this r here. Number 2, later in this course you'll learn about something called a Jacobian, which will tell you how to convert from rectangular to any coordinate system and tell you how to calculate what else will appear in the expression for dA. But for now, all you need to know is that when you convert from rectangular to polar, x becomes r cosine theta, y becomes r sine theta. Your limits of integration are whatever the range of values for the radius and the angle are. And this is the part that's easy to forget, the dA becomes r dr d theta. Stick an r in there. We're going to set up an integral in this video, and the next one we'll actually evaluate it, even though it says evaluate here. This is the integral from example 1 on page 711. We're going to evaluate this double integral, 3x plus 4y squared dA, over a region. And the region is defined to be the upper half of the plane bounded by the equations x squared plus y squared equals 1 and x squared plus y squared equals 4. You should recognize both of these as circles, both centered at the origin, this one with a radius of 1, this one with a radius of 2. So let's see if we can get this integral set up first by seeing what our limits of integration will be. If we were to draw both of these equations, there's the circle with radius 1, there's the circle with radius 2. Hey, it's a donut. But we want the region in the upper half plane, so up here on top, bounded by these 2 circles. So this is our region, a polar rectangle. The radius is between 1 and 2. This is the same one we had previously. and the angle is between 0, starting over here on the positive x-axis, rotates all the way over to the negative x-axis, so it's a rotation of pi radians. So that will define our limits of integration. But how do we actually set up the integral? That's actually pretty easy. For the limits of integration for the angle, it's between 0 and pi, and for the radius, between 1 and 2. Our theorem says that we replace each x with an r cosine theta. So instead of 3x, we'll have 3r cosine theta. Then we replace each y with an r sine theta. This y is squared, so the r will be squared and the sine will also be squared. And then for the dA, forget which of these lines is my boundary, so I apologize if this goes off the screen. I'm about to sneeze, excuse me. Excuse me, allergies. But for the dA, we would just replace it with r dr d theta. R dr d theta. Let me check real quick to see if that made it on the screen. It barely made it on. Nice job, me. So converting the integral from rectangular to polar is fairly straightforward. Honestly, the hardest part is determining the limits of integration based on how the region is defined. In the next video, we'll evaluate this integral, which honestly is a calculus 1 topic, even though it's a double integral. Make that calculus 2.